M. Victor Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to DTH channel, lecture 13 in astronomy and astrophysics. This lecture is about fundamentals of telescope. In this fundamentals of telescope, I am going to discuss scientific parameters of telescope, types of telescope used in astronomy, and various telescope mounts employed in astronomy, and discussion of the summary finally we are going to do. Human eye is a natural telescope. Human eye can produce a nice image if an object is in a particular distance in the sense, for a 20/20 vision, a human eye should be able to produce 1 centimeter object at a distance of 10 meter. So, human eye is a natural telescope. Beyond 10 meter, human eye cannot give a clear image of an object which is 1 centimeter in height. This is the ability of the human eye. To detect very faint sources which is very far, or to separate two closely located very far celestial sources, we have to use optical telescopes. If you get into the history of optical telescopes, the first optical telescope was used by Galileo Galilei in the year 1609. That is, in 16th century itself, Galileo developed the first astronomical telescope, and he used that telescope to view various celestial objects. His telescope is formed by the combination of a concave lens and a convex lens. This combination of concave and convex lens telescope is today known as Galileo telescope system. In that concave and convex lens is mounted nearer to the object. So, the front to convex lens is called an objective because it is close to the object being viewed, and the rear concave lens is called an eyepiece because it is closest to the observer's eye. So, Galileo's telescope system employs convex lens as an objective, concave lens as an eyepiece. This is the ray diagram of Galileo astronomical telescope system. In this ray diagram, you can see a convex lens nearer to the object, which is objective, and a concave lens nearer to the eye, an eyepiece. The distance between the convex lens and concave lens is called length of the tube. So, this ray diagram explains the Galileo optical telescope system. After the introduction of Galileo optical telescope in the year 1611, Johannes Kepler invented another type of longer telescope comprising 2 convex lenses known as Kepler telescope system. In Galileo telescope, some drawbacks are there: spherical aberration, chromatic aberration, like that. Various defects are there in the image produced by Galileo telescope. Hence, Kepler invented this telescope employing two convex lenses, the Kepler telescope forms an inverted image, but with a slightly larger field of view compared to the field of view of Galileo telescope. Earlier telescopes were made of simple glass lenses. When we use these simple glass lenses, the chromatic aberration, color aberration caused by the change in refractive index with wavelengths was a serious problem. To overcome this chromatic aberration, people kept on discovering, inventing new system of telescope. So, this is the ray diagram of Kepler's telescope. In this Kepler's telescope, you can see a convex lens as objective and also another convex lens as eyepiece. So, focal length of the objective is f0 and focal length of the eyepiece is fe. So, spherical aberration is also there in Kepler's telescope. Hence, further improvement was in need in the telescope invention. In the year 1664, James Gregory proposed a spherical error-free reflecting optical telescope with conic section mirrors known as the Gregorian telescope. But this Gregorian telescope was not put into practical by Gregory. Instead, Isaac Newton was the first one to construct a usable reflecting telescope. In January of 1670, he produced a much simpler optic system with a parabolic mirror and an inclined small flat mirror, today known as the Newtonian telescope. So, other than Galileo telescope, Kepler telescope, Newtonian telescope came into practice. This Newtonian telescope is a reflecting telescope compared to Galileo and Kepler telescope. Further improvement is made in Newtonian telescope. That improvement was done by a French optician N. Cassegrain. He came up with the third configuration for a reflecting telescope called Cassegrain telescope. Like that, the history of telescope, development in telescope has led the astronomers to view the celestial objects more clearly and more sharply. To understand the telescope more clearly, we are in need of certain scientific parameters. We need to understand certain scientific parameters. Those are all angular resolution of a telescope, magnifying power of a telescope, then f ratio of a telescope. This f ratio is common for all camera. So, these understanding about these parameters are very important to understand the telescope system more clearly. Now, let us see the angular resolution of a telescope first. The angular resolution of a telescope is its ability to resolve two closely located point objects. Human eye can produce a separation of 1 arc minute. That is the resolution ability of a human eye. This angular resolution term refers to sharpness of image produced by a telescope. That is, if a telescope has a high angular resolution, it will produce more sharper image than the other telescope in use. For example, with normal 20/20 vision human eye, we can read letters 1 centimeter high at a distance of 10 meters. That is the normal human eye angular resolution. With the Hubble Space Telescope, we could read the same size letter, that is 1 centimeter high letter, at a distance of 12 kilometer. So, if you use Hubble Space Telescope, you can read a 1 centimeter high letter which present at a 12 kilometer distance very clearly. That means 1200 times farther objects can be read, can be viewed using Hubble's telescope. This is the understanding of angular resolution. We characterize the angular resolution by the smallest angle theta that can be discerned in an image. For an eye with 20/20 vision, the angular resolution is 1 arc minute. 1 arc minute in the sense 1/60th of a degree. 1/60th of a degree means take 1 degree, divide that 1 degree into 60 parts. In that 60 parts, just take one part, that is 1 arc minute. So, human eye with a 20/20 vision, the angular resolution is 1 arc minute. If you take Hubble Space Telescope, it has an angular resolution of 0.05 arc seconds, which is 1200 times sharper than the human eye. So, telescopes are very important in astronomical observation. In that telescope, this angular resolution is more important, so that knowledge about angular resolution is very important. How can we calculate this angular resolution? There is a formula in physics to calculate the angular resolution. Theta is equal to 1.22 times lambda by d, where theta is the resolution in units of radians, because that angle has an SI unit radian. Degree is not the SI unit of angle. So, angular resolution is given in terms of SI unit radians. Then lambda is the wavelength of radiation in meters. Lambda is the wavelength of radiation in meters, and d is the diameter of the camera or telescope lens or mirror in meters. So, if we increase this diameter of the camera or telescope lens or mirror or objective, we can get less angular resolution. So, less angular resolution produces more sharper image. As we see here, the Hubble Space Telescope has an angular resolution of 0.05 arc second, but for a human eye, the angular resolution is 1 arc minute. So, high angular resolution means it's high angular resolution in the sense sharper image. If you want a sharper image, the angular resolution should be very small, in the order of 0.05 second. If you reduce that angular resolution further, then you can get more sharper image. Coming to the formula of angular resolution, wavelength is in the numerator. So, when you reduce the wavelength, when you decrease the wavelength, angular resolution will become more small. So, for ultraviolet radiations or for violet radiation, this angular resolution will be very small. So, sharper images can be produced for wavelengths in the order of 4000 angstroms or 400 nanometer or blue light. This is how angular resolution plays an important role in the parameters of telescope. If you use less angular resolution in the sense the angular resolution number is very small. If you use such a telescope, some binary stars in the sky can be resolved into two, or can be resolved very clearly with the telescope having high angular resolution. Then, what are the factors affecting this angular resolution? There are three factors which influences the angular resolution of a telescope. These factors are diffraction of the aperture, aberrations of the optical system, and atmospheric turbulence. These are all the factors which affect the angular resolution of a telescope. So, diffraction in the sense, if the diffraction at the aperture is small, then angular resolution, distortion in the angular resolution can be minimized. Then aberrations of the optical system. All optical lenses will not produce trouble-free, will not produce a trouble-free image. Some troubles will be there in the form of aberration, coma, and other defects in optics. So, such aberrations will also cause defect in the angular resolution. Then atmospheric turbulence, it's very common if you observe any celestial objects from Earth, because we can't predict the atmosphere of our Earth. It will not be stable. For minute by minute it will keep on vary. So atmospheric turbulence largely affects the angular resolution of a telescope. So in this image you can see the telescope which has less angular resolution, then a telescope which has higher angular resolution. That means this image appears as a single one, this appears as a double one. If you further increase the angular resolution, that means numerical value of angular resolution is reduced. Then this image can also be seen as two images. This is how angular resolution can be learnt for the telescope. The next scientific parameter of the telescope is magnification. How big a telescope can show an object. That's the meaning of magnification. This magnification of a telescope is the ratio between focal length of the objective to the focal length of the eyepiece. So focal length of the objective to the focal length of the eyepiece. This is the final expression to calculate the magnification of the telescope, more clearly learnt by looking at the optical diagram of Galilean telescope. So in this optical diagram, this red color image is the distant object. Y is the distant object. Then y dash, this is that y dash. This y dash is the real image from objective. This is that objective. This objective forms a real image at this point. Then this y double dash, orange color one or yellow color one, is the magnified virtual image from eyepiece. This is the final image produced by a Galilean telescope, final magnified image. The telescope magnification m is equal to FL1 by FL2. So this distance is FL1 and FL2, and this distance is FL1. So ratio between these two distances, that is focal length of the objective over focal length of the eyepiece. So this is the focal length of the objective and this is the focal length of the eyepiece. Ratio between that two give the magnification. And d, diameter of the objective, and small d, diameter of the eyepiece, that also will give the magnification. And tangent of the angle of inclination of the object, tangent of the angle of inclination of the eye. So here you can see that alpha 2, this is the angle of inclination of the eye. Then alpha 1, this is the angle of inclination of the object with the objective. So ratio between that two tangent will also give the magnification, which is equal to L by E. Then the exit pupil diameter d is equal to d by m, diameter of the objective over the magnification. So we can design exit pupil diameter using this formula. So virtual exit pupil distance of the L2 is L by m. Then distance between lenses FL1 plus FL2 can be obtained by knowing the focal length of the objective and the focal length of the eyepiece. Here objective is a convex lens, then eyepiece is a concave lens. That's why here minus sign comes for the focal length of eyepiece. This is how you can learn more clearly the magnification of a telescope. The same magnification can be applied for the reflecting telescope also. This is the magnification formula for refracting telescope. For reflection also same methodology can be adapted. Coming to the next scientific parameter of the optical telescope is F ratio, focal length ratio. To understand this F ratio, you must know the term aperture. Aperture is the most important specification of any telescope or any camera. This aperture is basically the measurement of the diameter of the main lens or mirror of the telescope. The size of telescope's aperture determines the amount of light entering into the telescope or light collecting ability of the telescope, and this light collecting ability is related by being proportional to the area of the lens or mirror used as an objective. So, aperture is an important parameter to calculate the f ratio of the telescope. The next thing is focal length. Focal length is a fundamental concept in physics. It's the distance from the telescope's optic lens to the plane in which the image comes into focus. That's the focal length of any lens. Coming to the ratio, f ratio is the focal length of the telescope divided by its aperture. This is the definition of f ratio. This f ratio parameter is an important one in understanding the telescope's ability. For example, the most common telescope designs is a 120 millimeter aperture, that is 4.7 inch refractor with a focal length of 1 meter. 1 meter in the sense 1000 millimeter. F ratio is nothing but the focal length divided by the aperture. So, aperture is 120 millimeter, focal length is 1000 millimeter. If you divide this 1000 millimeter by 120, it comes 8.3. It's more conveniently written as f by 8.3. This is the specification of f ratio of a telescope. The smaller the f ratio number, the lower the magnification, the wider the field of view and brighter the image with any given eyepiece or camera. That's the use of f ratio in telescope or camera. Faster f4 to f5 focal ratios are generally best for lower power, wide field observing and deep space photography. So, if you want to go for a deep space photography, that f ratio of the telescope should be between f4 to f5 and it should be fast. So, in telescope, smaller and faster tells about the time the aperture takes to open and close. So, that's the smaller and faster meaning. Then slow f11 to f15 focal ratios are usually better suited to higher power lunar, planetary and binary star observing and high power photography. So, if you want to go for deep space photography, you need to choose a telescope with fast f ratio between f4 to f5. If you want to go for lunar, planetary and binary star observing and high power photography, you have to go for a telescope f ratio specification of slow f11 to f15 focal ratio. Then coming to the medium f6 to f10 focal ratios will work in both the cases. So, this is how f ratio is another important parameter in understanding the telescope. So, magnifying power, f ratio and angular resolution are the three important scientific parameters of a telescope to talk about its ability. Now, come to the types of telescope. There are three types of telescope in use. The first type is refractor type telescope, then the second one is reflector type telescope, then the third one is Cassegrain telescope. Cassegrain telescope is a combination of refractor and reflector. Refractor telescope uses only lenses because lenses are refracting objects. So, these refractor telescopes are the most common telescopes we will be using. But nowadays in modern era, that Cassegrain telescopes are the most common one. These refractor telescope uses lenses instead of mirrors and the eyepiece is located at the bottom of the telescope. Refractor telescope design is similar to binoculars and most spotting scopes. Then It should be noted that images from refractors are mirror images and can be corrected using an erecting prism. This is the ray diagram of a refractor telescope. Objective and eyepiece both are refracting objects. Angle of inclination of the object, then this is the angle of view of the image through our eye. So, ray diagram of refractor telescope. What are the advantages and disadvantages of this refractor telescope? These refractor telescopes are easy to use and consistent due to simplicity of design. Then these refractor telescopes are excellent for lunar, planetary and binary star gazing, especially with larger apertures. Generally, these refractor telescopes have smaller apertures, typically 3 to 5 inches. Smaller apertures means poorer viewing of distant galaxies and nebula. Then another drawback of this refractor telescope is it will be heavy in weight and longer tube, that is the distance between the objective and eyepiece will be very long. Earlier 36-meter tube were used ancient days in 16th century. 36-meter tube were used by astronomers to construct a refractor telescope, and bulkier than reflector and Cassegrain telescopes of equal aperture. So, these are all photographs of modern refractor telescope. It is available in the market. Anyone can buy this refracting telescope and use it for lunar observation and other things. Coming to the next type of telescope, a reflecting telescope. This reflecting telescope utilizes a mirror instead of a lens, with the eyepiece being located at the side of the main tube. You look through an eyepiece on the side of the tube near up the top. This is the image of reflecting telescope. Here you can see the eyepiece. This eyepiece is side of the tube. So, the light from the distant object will fall on this primary mirror and it will get reflected by the secondary mirror and it can be viewed through the eyepiece. This is how reflecting telescopes are constructed. This reflecting telescopes utilizes mirror instead of lens. Then coming to the advantages of this reflecting telescope, usually have larger apertures, which mean excellent viewing of faint deep sky objects like remote galaxies, nebula and star clusters can be viewed using these reflecting telescopes. Then low in optical irregularities and deliver very bright images. Then a reflector costs the least per inch of aperture compared to the refractors manufacturing and catadioptrics, since mirrors can be produced at less cost than lenses. Another important and interesting advantage of reflecting telescope, that is mirrors can be produced at less cost than lenses. Coming to the disadvantages of this reflecting telescope, these are not generally suited for terrestrial applications. The tube is open to the air, which means dust on the optics even if the tube is kept under warps. So often we have to clean the tube, otherwise dust present in the tube may damage the image or light reflected by the reflectors. Reflectors may acquire a little more care and maintenance. This is the image of a reflecting telescope. The third type of telescope is catadioptric or compound telescope or Cassegrain telescope. This is a mixture of or hybrid of a refracting and reflecting telescope. This catadioptric or compound telescope were invented in the year 1930s out of a desire to marry the best characteristic of refractors and reflectors. They employ both lenses and mirrors to form an image. The greatest appeal of these instruments is in their commonly encountered forms. Two forms it is manufactured: Schmidt Cassegrain and Maxtrov Cassegrain. These Cassegrains are very compact. Then the tube of this Cassegrain are just 2 to 3 times as long as wide, an arrangement allowed by optical folding of the light. The smaller tube which is in use in Cassegrain is very light, and thus more manageable mounting can be done. Then the upshot is that you can obtain a larger aperture long focus telescope that are very transportable. But here too there are cautions, like the Newtonian Schmidt trigger Cassegrain telescope needs occasional optical collimation that lessens its appeal to those disinclined to the tinker. The field of view of this Cassegrain can be rather narrow too. In terms of price, aperture for aperture, this catadioptric lies midway between the reflector and the refractor. Like a Newtonian, the popular forms of compound telescope have a secondary mirror in the light path of the instrument. You can see that secondary mirror in the light path of the instrument. So even when a Schmidt Cassegrain or Mextrov Cassegrain will deliver very fine images of a wide variety of celestial objects. So this is the advantage of this is a schematic diagram of a reflecting Cassegrain telescope. Light from the distant object will fall on this reflecting objective, then that will be reflected back to the secondary mirror. Secondary mirror will reflect back and it can be viewed by the eyepiece. The secondary mirror can be separated, a small hole can be made to reduce the distortion produced even in this Cassegrain. Then coming to the types of mounts of telescope, two mounts are used by astronomers. One is alt azimuth mount, then another one is equatorial mount. In alt azimuth mount, you can see this is the simplest type of telescope mount. Altitude and vertical azimuth. Altitude is vertical and azimuth is horizontal. So both the direction the telescope can be rotated. This is the alt azimuth mount of a telescope. So if you move the telescope horizontally, that is azimuth axis. If you move the telescope vertically, that is the altitude axis. This is the alt azimuth mount. The next one is equatorial mounts. Equatorial mounts are superior and it can be used by interfacing the telescope with computer. Equatorial mount probably aligned with the axis of the earth. So this is the diagram of the equatorial mount. So here this is aligned to the or parallel to the axis of the earth, then right ascension movement of the telescope and declination movement of the telescope. This equatorial mount is used to view stars which are moving. So alt azimuth mounting and equatorial mounting are the two different mounting systems in telescope. This is how you can mount telescope. Then fork mount, this is the fork mount of a telescope. So in this lecture we have learned the fundamentals of telescope. Telescopes are an instrument used to detect very faint sources and used to separate two closely located celestial source. Telescopes are used. Galileo Galilei developed the first astronomical optical telescope. His telescope is formed by the combination of concave and convex lens. Then Kepler telescope came. Kepler telescope used two convex lens. Then Newtonian telescope came, which is the first reflecting telescope. Cassegrain telescope came. Then to understand the F ratio, magnification of the telescope, angular resolution of the telescope, we need to learn some basic concepts in physics. Those basic concepts are very useful to understand the telescope usages. Then three types of telescopes are there: refracting telescope, reflecting telescope and Cassegrain telescope. Then two types of mounting systems are there, because telescope mounting is very important to locate the celestial objects: alt azimuth and equatorial mounting systems. So this is how you can learn things about telescope, and you can surf this website to learn more about telescope. Thank you.